Hi all, I am excited to show you the final product of my research project. It is a web-based CPU simulator. I am Thilan, an engineer, currently works at WSO2 as an intern. This tool might be a great fit for anyone who is learning topics such as computer architecture, cybersecurity, or even reverse engineering, etc. And over the next few minutes, I am going to show you how this simulator visualizes CPU operations such as memory access, instruction execution, register updates, and stack manipulation all in real time. So let's jump into the introduction. Let's see what are the main components of this CPU simulator system. Here first we can see the memory section. We can see the memory addresses. These are the memory addresses, and we can examine each one by one. And here we can see the assembly instruction section. At this point we can't see any instruction loaded into the system. After we load some program into our system, we can see the instructions will be shown here. And also here we can see the console section. All logs will be displayed in this section. Also here we can see a clear button. We can clear our console using this button. And here we can see the program loader. We can use this load program button to load assembly instructions onto our system and execute those one by one. And we can see the reset button here. We can reset our CPU simulator to its original state using this button. And here we can see the execution controller section. We can execute one by one instruction using this execute button. Also, let's say we want to execute a custom assembly instruction in our system, so we can use this custom button and apply a assembly instruction on the go with this button. And at this point we can see the CPU registers section. I mentioned that we are using assembly into 64-bit architecture, so we can see the RAX, RBX, those are the general purpose registers, and also we can see the indicator registers, RSI and RDI, those are the source pointer and destination pointer indicators. And here we can see the stack pointer registers, RBP and RSP. RBP means base pointer, that is pointing to the base of the stack, and here we can see the RSP, stack pointer, that is pointing to the top of the stack each time. And in the 64-bit architecture, we know that we have some additional CPU registers called R8 to R15. So here we can see these also. And the most important registers is RIP register, that is instruction pointer. So we can see that one also here, RIP register. And also for the comparison operators and for jump in and those kind of things, we use RFlags register. So we can see that register here. At last we can see the examine memory section. Here we can see the stack section, .txt, heap, bss, data, and let's say I want to examine a custom memory address, so I can use this address button and apply a custom memory address. So those are the basic components of this system. Examine the stack area, that could be text area, heap area, data, or bss, anything. So I click this button, the stack button, so I can see the message is coming showing the stack area. So the memory addresses are changed. So this is the top of the stack and these are the bottom section. So I can click that section. So this should point to the top of the stack. So I can select any number of memory addresses. Let's choose decimal. So this is the top of the stack, and these are the another sections. This could be text section and anything. Not only the memory, we can examine registers also. Let's examine the RAX register. Here we can see the register examining component. Here we can see the whole RAX register. So we know that in the 32-bit architecture there was registers such as EAX, EBX, those are the 32-bit architecture register. So here we can see the this part of RAX register is taken as the EAX register. So in the 16-bit architecture we had AX register. So we can see that part here, AX register. So if we divide that into two sections, we can name those as AL section and AH section. So we can see all these sections in this examining register component. So currently that RAX register holds nothing, so there are some zeros. If we have filled this RAX register with the value, we can see that here. So let's see that later. let's execute some instructions and see what is going on under the hood. So if we examine the RAX register, we can see there is nothing on the RAX register. So let's execute a custom instruction. I will use mov rax 5. So we know that the destination is the first operand, and we call that this is the operation, this is operand 1, this is operand 2. So destination is the operand 1 in Intel architecture. So let's execute that one. So here we can see the move rax5 is the instruction, and here we can see the opcode. So 48, B8 and 05, this is the opcode for this particular instruction. So we know that the opcode for moving something to the RAX is this one, and what is the value of this moving instruction is 05. So here this opcode consists of that information. So we can see the log here pressing the instruction move with operand 1 is RAX and operand 2 is 5. So after that it is moving the immediate value 5 into the register RAX. So let's examine the RAX register. So here we can see 101 is now on the RAX register. So 101 in binary stand for 5 in decimal. So we can see that is working. So let's execute another instruction, move. First let's see what is the value of RBX. Here we can see 0. So let's move the value of RBX into RAX into RBX and RX. So currently RAX holds the value 5 and RBX holds nothing. So let's execute this instruction. So here we can see that instruction is also happening and executing. Let's examine what is the value of RBX register. So we can see that holds 5. So it is executing successfully. So here we can clear the console. Let's execute push instruction. So currently the stack, top of the stack, let's see, we can see the value is 0, top of the stack. So let's execute push instruction, push RAX. So we know that the value of RAX currently is 5. So let's use push instruction. So we can see the push RAX opcode is 15, and here we can see the RSP should be reduced because the that stack is going to the low addresses. So the value of the RSP should be reduced by 8 bytes. So here we can see it is reducing by from 71 to 63. So that means 8 bytes. So let's examine the stack again. So here we can see the value 5 is there. So let's use, so here we can see the value 5 is there. So we can see those are the custom instructions we can execute on this CPU simulator section. We only tried custom instructions, so we haven't added any set of instruction into our CPU simulator. So let's try a load in a program, real program. So first of all, let's clear the console and reset our CPU simulator. After that we can click this button. So here we can type our assembly instructions. Let's use mov rax3. So like that we can write our assembly programming assembly instructions here. After that we can click this button. So also we have some set of basic sample programs also. We can use this one if you want. So let's click this. So here we can see instructions are decoded. So at this point what we do is we assemble the instruction. This system consists of two sections called assembler and disassembler. So after that, after we enter this assembly instruction, the assembler is converting these assembly instructions into these opcodes and saving on the txt area. So we can see the txt area here. After clicking txt area, so it is showing the text segment. So that means this is the top of the text segment. Let's click this one. So let's examine hard drive. So we can see that move rax3 is opcode should be 48 B8 03 something like that. So we can see the text section contains that one. 08 B8 03 and that one. So the next instruction 48 BB. So let's see. So you can see 48 BB06. So that is this one, 48 BB06. So you can see how the text section contain the CPU instruction by assembler converting those assembly instructions into opcodes and storing that instructions in this text section. So after that, let's clear this one and we can execute these one by one. So let's execute first instruction. So first of all, let's examine what is in the RAX register. There is nothing, so the value is 0. So let's execute the first instruction. So we can see the instruction with move instruction, operand 1 is RX and operand 2 is 3 is executing. So it is saying that moving the immediate value 3 into the RX register. So let's examine what is inside the 3 RX registers. We can see that the value 3 is there. So we can do that. So the RIP register is incremented by 1. So that is why the pointer is coming to the bottom. So we can execute each and every instruction like that. So we can see this one. After we can execute this one. So we can see that all instructions have been executed on our CPU. So if we want, we can see the stack here. Also we can see any of the registers using this one. Let's see a practical example. Imagine that I am going to learn how the stack overflow exploit is working. So ultimate goal of this exploit is to override the RIP register and take control of the execution. And let's say this is the top of the stack and the overwritten RIP register, saved RIP register is value is stored here. So I can override the stack like this way.